All right, guys. So we're going to continue here looking at the consequences of special theory of relativity. And another consequence here is where we looked at the time dilation last time. So another one here is then the length difference, disagreement between two observers moving relative to one another. Okay. So imagine what we have here is you have you're in a moving, let's say, a frame. Let's say you're in an airplane, something like this. So what we have here is you are measuring then, uh, let's say, a meter stick. Okay, you're measuring meter stick. Obviously, then what I have here is length of the meter stick is 100 centimeters. Okay. So this length is measured by, let's say, by you in a reference frame of the airplane that is moving, for example, at 0.6 c. Let's say that. Let's say this airplane moving at 0.6 c. V is the velocity of the frame. Then measurement of the meter stick is done by you in the same reference frame. So then we can call this a proper length because you are measuring the meter stick in the reference frame. So that means that measurement is done in the same frame. So that's a proper length. Now, if then you have someone else on Earth looks at your meter stick and tries to make a measurement of the meter stick, then the length of the meter stick will no longer be 100 centimeters. So there has to be disagreement, just like there was a disagreement in terms of the time. That means 1 second for you will be, greater than, the time, for the observer. Remember, so that means the proper time is always less than the measurement of time from a, let's say different reference frame. Same thing now with the length. Okay, that means the distance for the meter stick will be measured to be different. Now, how different? Well, it depends how fast the reference frame S prime is moving. So remember, so this is S prime, and let's say this is a reference frame S. So that means one of the things we have here is that measurement done in reference frame S, let's say, will be equals to then um, 1 over gamma times then the measurement done in the reference frame where the experiment is done. Let's say S prime. Again, so you don't always have to have the proper length to be in S prime, right? So that means, for example, I did the measurement in S prime. That's why I call that the proper length. If the meter stick was on Earth, then that would have been the proper length. But the idea is, so let's say proper length is 100 centimeters regardless, right? Because that's you take the meter stick, you measure it 100 centimeters. It just right now it happened to be in the reference frame S prime. Then if I calculate the length measured by an observer on Earth, this will be 1 over gamma. Remember, gamma is basically 1 over square root. So remember, so it's 1 over square root of 1 minus v square over c square times LP. So basically 1 over 1 over that. So becomes then square root of 1 minus v square over c square times LP. Now let's see what we have. So if I plug in the value that I have, 1 minus 0.6 c over c squared times 100 centimeters, then see what we're going to get. That means the observer on Earth measuring the length of the meter stick um, will be 1 minus 0.6 squared, where gamma now is 0.8, then times 100. So he'll measure this to be 80 centimeters long. That means meter stick is only 80 centimeter long. Okay. Now, what happens if, let's say, then the meter stick was on Earth, right? And then you measuring for the, let's say, if the meter stick was here, 100 centimeters over there, then what will this guy measure? Well, it will measure the same thing. Now, the person in S prime would have been measuring then 80 centimeters. That means it doesn't matter where the, let's say, experiment is done. The idea is that if you're measuring from a different reference frame, you're gonna get then different length. Okay, so this is known as a length contraction, which means that length of an object measured in a reference frame that is moving with respect to an object is always less than the proper length. Okay, that means again, for example, if the meter stick was here 100 centimeters on Earth, and then you have an airplane moving with v is equals 2.6 c, that means if the guy here is measuring that meter stick that is on Earth in his moving reference frame, well, you get the same equation, right? That means proper will be here on Earth, so this will be proper. So then this will be then 1 minus 0.6 c over c square times 100, so it will still measure 80 centimeters. That means, again, what you will see here is the length of object measured in a reference frame that is moving with respect to an object, it's always going to be different. Now, so then how come there's a disagreement in this, right? Not a disagreement, but let's say, how come it works both ways? Well, it works both ways because you can always assume that, for example, if I come back over here when the meter stick was actually in the airplane moving at 0.6 c, we can say that for the airplane, we can always assume that this is zero, but s is moving with a velocity of negative 0.6 c. We can always assume that. That means we still have a relative motion. Because if you're in an airplane, you can say, you know what, I'm not moving. Earth is moving away from me at point C, just in the opposite direction. That means you can always have that this measurement is done from a faster moving, reference frame. Reference frame that is moving relative to your reference frame. So regardless if you're moving and they're stationary, or they stationary, or you're moving, there's a relative motion between you two. So that's kind of what we have. So that's another consequence of the specialty of relativity. Okay. So the observer who measures the proper length must be correctly identified. That's the key, because as I said, right? So generally in the problems like this, is the difficulty is identifying the who's the proper observer. Okay. So remember that the proper length between 2 points in space is always the length measured by an observer at the rest with respect to the points. See, that means if meter stick is in front of you in the same reference frame, that means you're measuring it, that means that's a proper length. Because for someone else who's moving relative to the meter stick, well, they're not at rest relative to the meter stick. So their length, their measurement of length is not proper. That's the key, right? If you are at the rest relative to the length of that, that basically the space, that you're measuring, right? Then that's a proper length. Proper length and proper time interval are defined differently. Okay. So the proper length is measured by an observer for whom the endpoint of the length remained fixed in space. The proper time interval is measured by someone for whom the two events take place at the same position in space. Okay. So again, make sure proper length, proper time is correctly identified in your uh, solutions, right, of the problems. All right, so here's sort of like, let's say, in terms of um, you can say the meter stick measured by an observer in a frame attached to the meter stick has the proper length. So, and the meter stick measured by an observer in a frame in which the stick has a velocity relative to the frame is measured to be shorter than the proper length. That means, for example, if this is in S prime, where you do the you're there making this measurement, then let's say this is the on Earth that is looking at the same measurement of or the same object, right? That measurement will be different because you are moving relative to that. Okay, so which means that length will be always shorter. That's the thing. The time measurement of a different observer always greater than the proper time, but for the length measurement is always less. So that's why length contraction. So always you measure smaller distance. That is why in the beginning um, of this lecture, remember I had this picture of the Mr. Tompkins where when he was moving at the speed close to the speed of light, that imaginary in the imaginary universe, right, where the speed of light was 10 meters per second, everything around him was shrinking because he was moving, and so he was when he was absorbing all the other objects they were not moving relative to him, everything was shrunk. So everything was, contracted. So the policeman was thin, the streets were shorter, and things like that. Because if you're moving at the speed that is closer or, compatible with the speed of light, then everything around you basically shrinks. Okay, if you start measuring other objects around you that are not moving relative to you, or basically there are uh, at the rest relative to you, you will measure things completely differently. All right, so let's look at a couple of examples here. So a friend passes by you in a spacecraft traveling at a high speed. He tells you that his craft is 20-meter long and that that the identically constructed craft you are sitting in is 19-meter long, according to your observation. How long is your spacecraft? How long is your friend's craft? And what is the speed of your friend's craft? All right, so let's see what happens here. So let break it down into like small parts, and let's say, so what happens in this example. It says that your friend passes by you in a spacecraft traveling at high speed. Okay, that means your friend is basically is S prime. U is S. Basically, you're going to be then uh, uh, inertial reference frame S. Okay. So let's say then your friend tells you that his craft is 20-meter long. That means he is measuring his craft to be 20-meter long, and he is at the rest relative to his airplane, right? He's basically in his airplane, so he can just measure from one length from one side to other. So 20-meter length that he measure is the actual length of the airplane. And then it says it then the identically constructed craft that you're in is 19-meter long. That means when he's moving and looks at your craft only is he is only measuring it to be 19-meter long. That means 19-meter is the measurement of your craft by him when he was moving away from you. Basically, he's moving, passes by you, right, at that high speed. Well, because that craft is identically constructed, that means you can assume that if he measures his 20-meter long, yours will also be 20-meter long. Okay, that means 20-meter is the length of the ship, regardless. Okay, he measures it to be 19 because he is moving relative to you, but he measures his own 20 meters, and he is at the rest relative to his own craft. That means yours, which is identical, will also be 20 meters. All right. Heartbeat says, how long is your friend's craft? Well, think like this. If you guys are moving relative to one another and you're both in the same identically constructed craft, and he measures yours to be 19 meters while he measures his to be 20 meters, then same thing will happen to you. You will measure yours to be 20 meters, but then you will measure his to be 19 meters because both of your length of the craft is 20 meters, and if he measures yours 19, you will measure his 19 because the speed relative to one another. That means for B, you will measure that to be 19 meters. Okay. Well, part C then says, okay, so then what is the speed of your friend's craft? Okay. Well, then for that, we have to then use the length contraction equation, which basically tells us that L is equals to, L proper divided by gamma. Okay. Well, what it means here is then, remember, we don't know V, right? We don't know how fast your friend is moving. We don't know how fast your friend is moving. But we know one thing is that we know that proper length is 20 meters. Okay. Because he will measure his 20 meters and you will measure yours 20 meters. But then we also know the length that both of you will measure of the other craft, which is 19 meters. Basically, this is then measurement by the other observer of your craft or yours by of his craft. That means this is L. That means we can then rearrange and solve for gamma, right? That means, gamma is equals to LP over L. Okay, so LP here is 20 meters. L here is then 19 meters. Okay. That means if I do 20 over 19, well, I'm going to get 1.05. Okay, you can also do other way around the ratio, but it doesn't matter. So 20 over 19, you get 1.05. Well, this is equals to gamma. That means 1.05 is equals to 1 over square root of 1 minus v square over c square. That means what you do from here is then just basically rearrange, right? So take the square root of both sides, basically square both sides. Then 1.05 square will give you, let's say, this is 1.1, let's say 1.10 is equals then 1 over 1 minus v square over c square. Then, basically take the reciprocal of it and then solve for v, right? So you should be able to do the, algebra here. V going to be equals 0.312c. Okay. That means, rewrite it in terms of, like, let's say c, you should get 0.312c. That means your friend is moving at basically that speed. All right. So next we're going to look at in terms of applying all this in getting more general, let's say, equation set to work with. Because one of the things we realized here is that using the Galilean principle of relativity, we can get speed that is faster than speed of light or lower than speed of light for the light if you do the measurements for the uh, different observers. But the specialty of relativity tells us that, well, all the observers should measure the same speed of light. That means that equation where we had x is equals to x prime plus v times t, or ux is equals to ux prime plus v, those equations basically break down. We cannot use them anymore. So then what we end up with here is with um, Galilean transformation equation must be modified. For that modification, then we're going to be then using what we call Lorentz transformation equation. Okay. That means what we have here is the observer in frame S represents XYZT. Those are the measurements of the observer in frame S. And observer in frame S prime represent X, Y, X prime, Y prime, Z prime, T prime. Okay. So then if two events occur at point P and Q, then the Galilean transformation, remember, would predict delta X equals delta X prime, which is basically the distance between 2 points in space at which the event occur, does not depend on the motion of the observer. Okay. But obviously, they're not valid when the speeds are very large. So any type of speed where v approaches c, they're just break down. Okay. So we need a new type of transformation equation, and they come from Lorentz. So Lorentz transformation equation basically modify that. So instead of x is equals to x prime plus vt, well, we add gamma into the fold. That means it's gamma times x prime plus vt prime. Then y and equals y prime, let's say, agree because we only have a horizontal motion. Z equals z prime, agree because, again, we have a horizontal motion only. But then time is no longer in agreement because of the time dilation. So we apply that. So then we have new equation for the time. T is equals to gamma times t prime plus v over c squared x prime. Okay, so this is valid for any type of speed as long as it's less than c, because if the v is greater than c, right? So again, you're not gonna have correct answers, and there's no such thing as v being greater than c, and even v is equal to be c, because we only going to be talking about, let's say, object going at the speed that is close to the speed of light, but not at the speed of light, because only light can move at the speed of light. So no object can ever reach that speed. Okay. So, and one thing we have is that the t prime depends on the t and coordinate x. Okay. That means what we have here is then now this new factor, right? Gamma comes into play. Okay. Again, and, what we get here is time and space are closely interwoven, so we call it space time, and the transformation coordinates, this is for the position, this is for the time. Those are the one that is modified because of the length contraction and time dilation. Well, obviously then we also have to modify the velocity equations, because now if I take the derivative of this one, I'm not going to get the same derivative, right, as before. So if I do dx dt and d dt of this whole thing, right, remember now I have a factor of gamma. So I mean, we are doing technically that we're taking the derivative of that. It just becomes a little more complicated to take in the derivative of that. But in any case, so let's say you take both of them, ux, ux, doing ux, doing dx prime, and eventually getting this, let's say, equations for the uh, velocity of the object for both reference frames. Okay, remember, so then x equals x prime plus vt then times gamma. Then you can pretty much rearrange that to get for the uh, you know uh, x prime as well, right? So for example, dx prime equals gamma times dx minus v dt. So then taking the derivative of that, what we're going to see here is basically solving for ux prime. So taking the derivative of this, and in terms of where dt prime is equals to that. In any case, so the derivative eventually gives us equation for the position, for the velocity of the object relative to the, in terms of measured in s, right? So what we have here is that ux prime is equals to this ux is always the measurement of the velocity in the reference frame s. Ux prime is always the measurement of the velocity with respect to reference frame s prime. Okay, and then equation is pretty much will give you the measurement. So for example, this is reference frame s. Oops. And this is reference frame x s prime. So for example, if you have an object moving here, this will be ux, and then this is your friend. Then if your friend measures the velocity of that object, you have to use this equation to calculate its speed. That means this will be the equation to calculate the speed of the object relative to your friend who's in the s prime reference frame. Okay. Now, same thing we can do for the vertical and along the z-axis. Okay. So, which is basically in terms of the um, something that we almost never do, but let's say those are the equations for the horizontal, vertical, and z component of the velocity. Okay. Obviously, then we can rearrange and solve for the velocity relative to the s reference frame, right? So you basically have both of them, right? So this is if you want to, let's say, you're in a reference frame s, you want to measure the velocity of something. This is the equation for that. And if this is your frame is measuring in the moving reference frame s prime, then equations you can see, right, is slightly different. So then it's important for you to understand the difference between them. Okay, so that's basically then the equation. So this is thing like this. This is you measure, or you not calculate. Let's say calculate in reference frame S. And this is, let's say, your friend calculates relative to S prime. Okay. Excuse me. And that's kind of what we have. That means you can use both of those equations, and now they are taking into account relativistic effect, right? The consequences, and these are more general ways. That means now you will never get a value that is greater than speed of light or less than speed of light for light, right? So you're always going to get the correct answer. One thing we can do here is we can verify. So let's say here's reference frame S, X and Y. And this is, let's say, you are using a flashlight and you have a light moving at the speed of C in your reference frame. Then here's your friend looking at that light, but your friend is moving with velocity V away from you. Okay. The question is that, will you calculate same speed C for the light? Well, let's see. Remember, what we're going to do here, we're going to measure this speed as ux prime, because your friend is measuring this or calculating. That means we can say that, okay, we are ux prime represent your calculation of the velocity of light. Well, let's see. Ux prime, that means I'm using this equation over here, is equals to, well, ux represents measurement of u in your reference frame, which is basically C. You're saying my measurement of speed of light is C. That means ux is then C minus V divided by 1 minus ux times V. Well, ux is C times V over C squared. Well, in this case, this C cancels out one of them. So then what you end up with is C minus V over 1 minus V over C. Now, what I can do here, I can then say this is C minus V over, kind of like multiply that. So it becomes C minus V over C, which then you can see, right? So if I move this one up, becomes C times C minus V over C minus V. They cancel each other, and you get C. That means your measurement of the light is also C, same as your friend's measurement. So that means both of you agree on measurement of light. Both of you measure or calculate C to be the speed of light. All right, so let's then look at another example. A base on planet X fires a missile toward an oncoming space fighter. The missile's speed, according to the base, is 0.5 C. The space fighter measures the missile's speed as 0.96 C. How fast is the space fighter traveling relative to planet X? All right. So then what we get here is this. So obviously planet X is the reference frame S, right? Planet X is our, reference, so the reference frame is S. Then the space fighter is then going to be S prime. Okay. It just happened to be moving to the left, right? So basically it's moving like this. All right. So, but that's something we will then eventually measure. Here's then what we have. Let's say there's a missile, right? Missile has two different speeds given to us. So once the planet X fires the missile, relative to planet X, that means relative to someone here on planet X, the measurement of the missile is 0.85 C. Remember, that means what I have is that U represents the measurement, right, of the missile relative to the someone on planet X, which is frame S. That means it's 0.85 C. Then someone else in a S prime reference frame measures the same object moving at ux prime, right? So as a 0.96 C. Okay. which is understandable, right? So there has to be a disagreement in terms of that. Okay. So then what we have here is the question is that how fast the space fighter traveling relative to planet X? What is the velocity that we want? Is velocity v, because the space fighter is the moving reference frame s prime. So all we want to know here is how fast that reference frame is moving, which is v. Okay. Now we're given the that's why what we do here is we are just basically using that two measurements of the uh, a missile, which is ux and ux prime, then to calculate the v, because what we're saying, we have measurements of missile with respect to both observers, one on earth, one on in the spaceship. Then we can use that both of those together to do this calculation. So in a way, it doesn't really matter which one we're using. Are we using the first equation or the second equation? Well, both equations are pretty much the same for us, right? So because we're given both of those quantities, and we know that let's say those two already enough for us to do the calculation, because both equations have they have u prime, and they have v, right? So then you can just basically do either way. All right, so let's say here we have u prime is equals to u minus v. Let's say you can put the subscript, and then 1 minus ux v over c, or c squared. Okay, so that's the equation, right? So again, you can use the other equation as well. But in terms of here, we have this equation. Our goal here is to find v, right? It's just a little bit of tedious algebra. But one thing we can do here is we can cross multiply. So then ux prime times 1 minus ux v over c square equals ux minus v. And then basically do some more algebra. So over here we have ux prime minus, it's kind of like distribute, right? Ux prime times 1, then minus ux prime times ux v over c square, then equals to ux minus v. Then one thing we can do here is move v to this to the left and ux prime to the right, because we want to solve for v, right? So basically move everything with v to the left. So then becomes v minus ux prime ux v over c square equals ux minus ux prime. And then from here, basically factor out v times 1 minus ux prime ux over c square equals ux minus ux prime. And then just divide both sides by that, right? 1 minus ux prime, sorry, ux over c square. Cancel those, and then you're solving for v. All right, so let's do this. V is equals to ux minus ux prime. Well, it's 0.85 c minus 0.95 c, 96 c, then divided by 1 minus then ux prime times ux, right? So ux prime times ux. So 0.85 c times 0.96 c over c squared. So c squares cancel out. Do the calculation, we're going to get 0.60 c. All right, that's the answer for that. Okay, basically we calculate the speed of the space fighter to be 0.6 c, and the direction to be negative because it's moving to the left. All right. Next, we're going to talk about some other uh, physical concepts that need to be modified because of the relativity, mainly momentum and energy. So for the momentum, what we have here is that, and the reason we're doing this too, because there's a conservation of momentum and conservation of energy, right? Those two very important, let's say, physical concepts that we learned that, we have conservation laws for. So one thing we had is that says that to account for conservation of momentum in all inertial frames, definition must be modified to satisfy this condition. So we have the linear momentum of an isolated particle must be conserved in all collision. So the relativistic value calculated for the linear momentum of a particle must approach the classical values as the particle speed approaches zero. Okay. Remember one of the things we had about um, the Newtonian mechanics. There was no limit for the speed. Well, if you have no limit for the speed, that means in a way you have no limit for the momentum. But there is no such thing, right? The even light has a limit for the momentum it can have, right? So if you're talking about a particle of light, for example. But the idea here is that um, there has to be modification, and modification is basically taking momentum, which is m times velocity, and multiplying that by this gamma factor. Okay, so momentum here is now equals to then gamma times mass times the velocity. U again representing the velocity of a particle. So this is a relativistic momentum, and obviously one of the things we have here is that gamma here then uh, provides that limit, which means that the speed and momentum will never going to just increase exponentially. So at some point you get some kind of maximum value, which then eventually kind of like saturates. All right, so that means one of the things you have here, you do get some kind of maximum value for those things. Okay, so but obviously then remembering that this is the equation for that, right? One thing we have here is to change the momentum. If you remember, there was always a force needed to change that. So then this force is now a relativistic force because there's a relativistic momentum. Well, we have a relativistic force. So then F equals dp dt, which means that you take the derivative of that with respect to time. Okay. But then one thing we have is that when you talk about dp, which is equals to force times dt, okay. So then, in a way, what one of the things we have here, we can see, right? This force has to be relativistic, right, in order for that to happen. In terms of then the speed of light, is I mentioned already is the limit of our universe. There's nothing that at least we have measured or observed that can move faster than speed of light. And um, some experiment that were done that came out, the published or came out that we found something that is something that's moving faster than speed of light. Eventually came back and said, okay, so we just made a error here or error there or mistake here, and so on and so forth. So far, we haven't had anything where you know that can move faster than light. Um, and one of the things we have here is even that, as I said, right, only can be achieved by light. That's because we think of light as something that doesn't have mass. It's a massless, it's a massless thing, right? So the light is just pure energy. So you can see that it is the maximum speed possible for matter, energy, and information transfer. Any object with mass must move at the lower speed. Okay, so that means pure energy can go at the speed of light in vacuum, c, but anything that has matter has to move at a little bit of slower rate. Let's look at here an example, which is a linear momentum of an electron. Well, electron, we know that is it has mass as small as it is, right? It has a mass of 9.11 times 10 to the negative 31 kilogram. Moves with a speed of 0.75 c. Okay. We can actually have electrons and protons move at much higher speed. This is not a limit at all by any means for those. We can have the protons and electrons move at 0.99999 c and things like that. So we can make them move very fast, smash them into together, and then basically create some of those exotic particles. In any case, find the magnitude of its relativistic momentum and compare this value with the momentum calculated from the classical expression. Okay. Well, classical expression is very straightforward, right? So let's actually do that first. P is equal to just, m times u. So mass is 9.11 times 10 to the negative 31 kilograms, then times the speed, 0.75 c. Well, I calculate this, we should get 2.05 times 10 to the 22 kilograms meter per second. Okay, so that's what I would calculate for the uh, classical a relativistic, sorry, classical momentum. Relativistic momentum, so C for classical, R for relativistic. So then this becomes, uh, in a way, this value, right? So basically I have me times u, then divided by times gamma, which is then divided by 1 minus v square over c square. So 9.11 times 10 to the negative 31 times 0.75 times 3 times 10 to the 8 meter per second. That's what c is, right? Then divided by square root of 1 minus 0.75 c over c. I just keep them here because I can just cancel them like that. So what we calculate, we get 3.1 times 10 to the uh, negative 22 kilogram. Okay. Which means that what I have here is this is 2.05 and this is 3.1. So roughly 50% increase, 50% greater value, because these are more corrected relativistic values compared to the basically wrong classical values. Okay. All right, so one thing we have is if the force is relativistic, whenever this force, relativistic force, does work on a particle, right? Well, then there's energy associated with that. Remember, work done by a force basically can change the energy of the system. So then we can think of, like, let's say then that work can go and change the kinetic energy of the particle. That means now we have relativistic modification to the energy approach as well. Okay, so let's look at then a work done by a force acting on a particle, and it's equal to the change in kinetic energy of the particle. Let's say initial kinetic energy is 0, object starts from rest. Then the work done is equal to delta K minus 0. And, sorry, delta K, where then final K, let's put like final K minus initial K is 0. That means what we're saying is that all the energy sort of like goes as a kinetic energy. So like, let's say, well, it's equal to then, if you remember, the equation for the work done is F dx, right? So let's say horizontal, going from x1 to x2. That's the equation here that we have. But this is a relativistic force, which is then equals to then dp dt, right? That means what we have here is equation basically lets us look at in terms of um, looking at the relativistic effect. So again, F dx from x1 to x2 equals an integral from x1, x2, then dp dt, which is then the force dx. All right, so now one of the things we do here is we know that P is equals to m times, sorry, it's a m times u over square root of 1 minus v square over c square. That's basically the relativistic momentum. So then if I'm doing then dp dt, then this will be then d dt of mu over 1 minus u square over c square. Okay. So then if we take the derivative of that, what we'll get here is basically, rearranging this. So I get m 1 minus u square over c square 3 halves du dt. Okay. So that means now if I take this and bring it here, where it's integral going from for m, then 1 minus u square over c square 3 halves, and du dt. So then for I have here is basically going from 0 to t, and then I took, like, let's say u dt, where then dt will cancel out, and that u dt comes directly from dx. Remember, what is dx? Dx dt is equals to u, so then dx is equals to u dt. Okay, so then you can just plug in there and cancel dt. So then you have then equation where you have then basically in terms of just u. So then this becomes m 1 minus u square over c square 3 halves, then du. where now the limits becomes then from 0 to m, from sorry, 0 to u, because now you uh, integrating in terms of du. Anyways, so if we do this integral, work done is equal to then we end up with mc squared divided by square root of 1 minus u squared over c squared minus mc squared. Okay. So since work done was equals to then kinetic energy, that means kinetic energy is equals to that. Okay. So remember then 1 over square root of 1 minus u squared over c squared is then gamma. So then we can just say that this is mc squared times gamma minus mc squared then equals to k. Okay. Or factor out gamma, so it's gamma 1 minus mc squared equals to k. That's then the equation for the kinetic energy. Okay, so relativistic kinetic energy. So you can see it over here. So mc squared, this mc squared quantity, right, is known as the rest energy. So this one is over here, mc squared. That's the rest energy. Gamma times mc squared is actually end up being, so you can see, right? So kinetic energy is basically gamma mc squared minus mc squared. Okay, that means gamma is equals to then mc squared plus the kinetic energy, which means that gamma is that some energy plus kinetic energy. That means sum of two different type of energies, rest energy and kinetic energy. That means it has to be then the total energy. So this gamma times mc squared then is the total energy of the system, so of the object, and depends on the speed and its rest energy. So you can see, right, at low speeds, where the speed is much, much less than speed of light, this reduces to the classical result of 1/2 mc squared, 1/2 mu squared. Okay. But then at the higher speeds, right, your kinetic energies then basically has this as the equation that required for us to use. Okay. That means this is basically give us that in terms of you can say, right, this graph gives you the red as a relativistic calculation, shows correctly that u is always less than c, where this is basically 1.0 c. And then non-relativistic calculation, which is 1/2 mu squared, predicts parabolic curve and the speed u grows without limit. Okay, that means there is no limit in terms of classical prediction, and there is a limit if you use the relativistic correction. So then the last set of equation we're going to be looking at is, again, as I said, right, so this is total energy, which is gamma times mc squared. So that's the sum of kinetic energy plus rest energy. So usually written like this, ER, rest energy. So so this rest energy is what we use for the most famous equation in physics, right? E equals mc squared, which shows that mass is a manifestation of energy, which means that for us, energy and mass are technically this, the same thing, right? So you can have all the mass of the object converted to energy, or all the energy of the object converted into mass. That means you can create matter from energy or energy from matter. And that's something we have always observed. You can, one of those things that they do in those um, particle, let's say accelerators, they smash particles together, and some of their mass is actually converted into energy, and that energy then can actually be used up to create some exotic particles, like um, let's say Higgs boson or something like that. So and we also have seen that you can generate an electron from two photons. Photon is the light. You can have two photons smushed together, and then they can be converted into electron. So which is incredibly, if you think like it's such an incredible result. That means from pure energy you can create an electron, something that has matter. But in any case, so uh, that's kind of like what we have. So the energy and mass are basically two things in different form. Okay. One thing we have, the last equation here is since gamma mc square, and P, which is momentum gamma times mu, are related to each other. We can just put them again in the same equation, where E squared equals P squared times C squared plus mc squared squared. So so then when the particle is at the rest, P equals 0. So then the energy is basically just the rest energy of mc squared. Okay, that means when we say equals mc squared, is generally um, we only talk about, like, let's say rest energy, right? So not necessarily the total energy of the system and things like that. So rest, when energy equals to the rest energy, right? When E is equals to mc squared, that means we're talking about object that is not moving. It doesn't have a momentum or doesn't have a kinetic energy. All right. So here's sort of like what we have: mass and energy. When even when a particle is at rest, it still possesses enormous energy throughout its mass. So generally, when we would have object as at rest, we would say that there is no energy in the system. But obviously, that is not true. It now has what we can call rest energy, because you can see, right, rest energy just depends on the object, to have a mass, and c is just the speed of light, right? So it's just a constant. So you can see, right, experimental proof of the equivalence of mass and energy occurs in nuclear and elementary particle interaction, where the conversion from mass to kinetic energy takes place. When using conservation of energy, rest energy must be included as another form of energy storage. This becomes particularly important in atomic and nuclear processes. Okay. Now let's look at um, this one last example. So in a certain reference frame, a particle has a momentum of 6 mega electron volt per C and a total energy of 8 mega electron volt. All right, so remember, electron volt is a unit of energy, right? It's a unit of energy, and usually we use that when we talk about very small particles, where 1 electron volt was equals to 1.6 times 10 to the negative 19 joules. That's the equivalent. So determine the mass of the particle from the given information. So let's do one at a time, right? So it says in a certain reference frame, a particle has a momentum of 6 mega electron volt per C and the total energy of 8 mega electron volt. That means we're given two values. See, this is just mega electron volt. That means that's a unit of energy. This one, mega electron volt of C, that's a unit of basically a momentum. Okay. And one thing we know here is for part A, right? Mass, or thing like this. So let's say the total energy, right? So then the total energy equals to remember, so it's P squared times C squared plus mc squared squared. So we basically have this equation over here. So then what we can say here is that mass, of the particle is equals to rest energy divided by c squared. So we need to then go ahead and calculate the rest energy first. That means here we can say that P squared C squared plus rest energy squared, which means then, let's say we'll come back to this. So rest energy squared then is equals to total energy squared minus P squared and C squared. So then we can take the square root of both sides. So then this will be equals to square root of 8 mega electron volt square minus 6 mega electron volt per C squared times C squared. And then we can calculate the rest energy from here, where we can just cancel the C squared. So this is like that, sorry. So rest energy is equal to 5.292 mega electron volt. if we do this calculation, then I can come back and solve for the mass. So it equals to then the rest energy, 5.292 mega electron volt divided by 3 times 10 to the 8 meter per second. But we need to convert this mega electron volt into um, joules, where I can rewrite mega as times 10 to the 6 electron volt, and then 1 electron volt is 1.6 um, 1.6, so 2 times 10 to the negative 19 19 joules. So we can calculate this. So this should be actually squared. So I get 9.4 times 10 to the 30 kilograms. So that's basically the mass of the particle. All right, so part B says, what is the total energy of a particle in a reference frame in which its momentum is 4 mega electron volt per C. So we can do that over here. Here's part B. So for this one, again, we have a E squared is equals to P squared times C squared, then plus M C squared squared. Okay. So this will be then in terms of the energy calculation. So now one thing we know here is that um, energy, this one is like writing P squared C squared plus then the rest energy square. So we assume that the rest energy is the same, it's just momentum is different. So we can calculate this as square root of. So momentum now is basically 4 electron volts per C rather than C. So becomes 4, mega electron volt per C square times C square per C. But this is into square, the C square is going to cancel out. Then plus the rest energy, which is 5.292 mega electron volt. Calculate this, we should get 6.63 mega electron volt. All right, so part C then is asking what is the relative speed of the two reference frames. That means what we need to find is basically V. V is the velocity of one frame relative to the other one. Okay, that means for part C, we are solving for what is V. Okay. Now, one of the things we know here is that the equation generally that relates those is U equals U prime minus V over 1 minus UV over C squared. So U prime V over C squared. So this is the equation that relates the speeds, right, in two different reference frames. So then from here we can rearrange and then try to solve for basically V. That means first we need to find what is U, what is U prime, and then plug it into this equation, rearrange it for V, and solve for V. Okay. So let's say then if I rearrange this equation for V, then V is equals to, again, so some algebra, right? So cross multiply and then the solve for V. V is equals to U prime minus U divided by 1 minus U prime U over C squared. So I showed you this, in the previous example. So using this, as I said, right, so our goal will be to find those values of U and U prime. Okay. So we will then take the equation for the reference frame, the first reference frame. Um, Remember, so we have two reference frames, and the difference here is that the momentum in one is 8 mega electron volt, and then the momentum in the other one is 4 mega electron volt per c square. So those are the two two differences that we have. So let's say right now in the first reference frame, we can say, let's say in terms of S, right? So this will be um, E is equals to, okay, so let's say this one actually the S prime. So E is equals to the, sorry guys, I think I got this wrong. So this should be actually in terms of U prime equals U minus, so that's the equation. So like this. All right, so that means just so it's U minus U prime, something like that. So just modify a little bit. Uh, okay. So then if we do these calculations, we can look at it in terms of, so E naught basically divided by square of 1 minus U square over C square. So this is then equals to C square of 1 minus E naught over E squared. Well, let me kind of like, so that means if I cross multiply and solve for U, that means using this equation. And this one, I'm basically saying that this is where total energy is equals to gamma times the rest energy, right? So remember, so the equation was equals gamma times mc squared. That's the total energy equation. So then I'm rearranging and then solving for U from here. So U is equals to C times square root of 1 minus uh, rest energy over E squared. Okay. So then I can calculate this where this is C, 1 minus the rest energy 5.292, and total energy is 8. Both of them are mega electron volt, which are going to cancel out. We can then calculate this to be 0.7499 C. That's the value for U. Then for the second one, which is for the S prime, so we can then, one information we know here is about the momentum. We know that momentum is 4 mega electron volt. So then we can use this equation for the momentum, where P is equals to gamma times M times U prime. So again, rearranging, where then gamma here is 1 over square root of 1 minus U prime over C squared times M times U prime. So then we can solve for U prime, which will be equals to P times C, then square root of P squared plus mass times C squared. So basically the rest energy squared. Okay. So if I take this and if I do the calculation, so this is 4 mega electron volt per C times C cancels out, then square root of 4 mega electron volt square per C, then plus 5.259, let's say square, in any case. So like, let's say then we're going to get U prime, I have no space there. So 0.60306. So that means now that I have both U and U prime, I can come back and solve for V. V is equals to 0.7499 C minus 0.6030 C divided by 1 minus 0.7499 C times 0.06030 C divided by C squared. Then we can get V as equals to 0.268 C. Okay. That will be then our value of velocity of one frame relative to the other one. Okay, that means, you can say that, for example, S prime reference frame is moving with 0.2868 C relative to the other one. All right, so here one last example. In reference frame S prime, two protons, each moving at 0.5 C, approach each other head on. Calculate the total kinetic energy of the two protons in frame S prime. Calculate the total kinetic energy of the protons as seen in reference frame S, which is moving with one of the protons. All right. So we are basically asked to find the kinetic energy. Okay. So in terms of then finding the kinetic energy, we can see that um, we have the value, right? So let's say I can write each moving at point C. So that means we are given the speed. Remember, so when you're talking about speed of 0.5 C, approach each other head on, that means, they're moving toward each other, right? One is, so you can say that, let's say ux is equals to 0.5 C, and let's say in terms of, like, let's say then, or the first one, like, let's say, right? So let's say ux prime, because this is, in the reference frame as prime. So ux1 prime is equals to 0.5 C. Then ux2 prime is equals to negative 0.5 C. Okay. So think like this. So here's a reference frame S with X and Y. Then here reference frame X prime, S prime, where this is Y prime and X prime. So it says then in the reference frame S prime, they're moving at 0.5 C head on. So we want to calculate the kinetic energy of the two protons in frame S prime. Okay. That means first we want to look at in terms of kinetic energy in this frame. One thing we know here is that kinetic energy is equals to um, gamma minus 1 times then the rest energy, right? But this is basically for each one of them. And then the total kinetic energy is equals to, let's say, K1 plus K2. Okay. That means, each one has a gamma minus 1 times rest energy. So it's 2 times gamma minus 1 times rest energy. Okay. That means I can calculate the kinetic energy as 2 times gamma minus 1, where gamma here is 1 over square root of 1 minus the speed is 0.5 C over C squared minus 1 times m times C squared. Okay, so let's first look at in terms of, let's say, mc squared, right? So we know it's a proton. So we know that the mass of the proton is basically, a given to us. So we can plug in that as well. So let's say I can say, all right, so then mc squared is equals to mass of the proton, which is 1.67 times 10 to the negative 27 kilograms times 3 times 10 to the 8 meter per second square. And then we multiply this with, as I said, right, most of the time we do electron volt. So 1.60 1.602 times 10 to the negative 19 joules is 1 eV, electron volt. So we can calculate this quantity to be, let's say, 930, let's say 938.3 mega electron volt. Okay, that means this is just, m times c squared, the rest energy. So I take this value and plug in over there for the kinetic energy. So I can calculate kinetic energy to be 290 mega electron volt. Okay, it's 290 mega electron volt. All right, so then the next, what I have here is part B is asking, calculate the total kinetic energy of the protons as seen in the reference frame S, which is moving with one of the protons. Okay, that means one thing we want to do here is we want to find basically the velocity of, let's say the proton that can be seen or measured from the reference frame S. And obviously one thing we have here is that this value here is, 0.5 C, right? That's the value measured relative to S prime. Okay, so that what we do here is, let's say for part B, so we need to, pretty much use the same equation, but we need to then find a different value of the speed for the protons. So then let's assume, like, let's say this is that, other proton. So that means this frame is moving with speed of c, sorry, 0.5 c. So this is 0.5 c. Okay. So that means this is moving at 0.5 c, and we can then just assume that if you're here in this reference frame S prime, so then you can think like, let's say this guy, right, ux prime, you will measure then this to be 0.5 c. Okay, because you see the proton moving toward you at 0.5 c, so you basically measure that to be a 0.5 c. So we take u is equals to ux prime plus v over 1 plus ux prime times v over c squared. So then ux prime is 0.5 c plus v is 0.5 c, then 1 plus 0.5 c times 0.5 c divided by c squared. All right, so we do this calculation. So we're going to get then 0.8 c. That means the value of the velocity relative to reference frame S is 0.8 c. Well, that means now that we have this, we can then go ahead and calculate then the kinetic energy. So we can find gamma from that, which will be then 1 over square root of 1 minus um, u square over c square. So if I plug in this, then we can calculate, plug in the value of 0.8. So we're going to get 1.67. And the kinetic energy is then going to be gamma minus 1 times then the rest energy. So then this will be 1.67 minus 1 times rest energy of 938. And then we're going to get then kinetic energy of 629 mega electron volt. All right, so that's then the value of the kinetic energy of the proton as seen from the reference frame S. All right, so that's it for this chapter.